Let us start chapter 6 module 2. In this module we shall give a quick review on topological groups. In fact, we have seen in our previous module quotient spaces formed by the help of partition or equivalence relation. Using the action of topological group on topological spaces, we can also define partitions. For this reason, we require the notion of topological group to give some other ways to describe quotient spaces. We will start with the definition of topological group. So, what is topological group? In fact, topological groups contains two structures, topological structure and group structure. We have seen the examples of topological groups in many cases. For example, our most known mathematical structure R. We know that R has a topological structure as well as a group structure. That is, R plus is a group and R with the usual topology is a topological spaces. Now, if a mathematical object has two mathematical structure, there must be some connection with these two mathematical structures. In case of R plus and the topology of R, this connection is described by the continuity of addition and continuity of making negation. That means the addition function from R cross R to R is a continuous function and negation function from R to R is also continuous function. In general, by a topological group we shall mean a group with a topological structure where the group operation will be continuous with respect to this topological structure and the inverse operation will also be continuous with respect to this structure. Let us view it in the slide presentation. As we have discussed in the introductory discussion, let us formally define topological group. By a topological group, we mean a group G equipped with a topology with respect to which the group operations are continuous. That is, the mapping xy goes to x dot y from G cross G to G is continuous and x goes to x inverse is continuous from G to G. One of the most important topological group is Z plus, where Z is equipped with the discrete topology. Another example of topological group which I have already mentioned is R plus. Both of these topological group in fact are local compact topological groups. In fact, by a local compact topological group, we mean a topological group which is local compact in its topology. So, what is the advantage of topological group? In fact, for topological group, it is sufficient to know the behavior of topology near the identity. or we can say at the point identity. That means we don't require to know the local behavior at every point of the topological group, which is not true in case of general topological spaces. These holds becomes topological groups are homogeneous. Homogeneity comes from the left operation and inverse operation. Let us state it formally. Let G be a topological group. Then the topological of G is invariant under translations and inversions. That is, if U is an open set, then so are XU and UX and U inverse for any X belongs to G. Moreover, if U is open, then so are AU and UA for any subset A of G. To prove this, let us consider the left multiplication defined by lambda x of y is equal to x dot y for all y belongs to G. It can be easily observed that for each x, x dot y is a homeomorphism. That means for each x, the left multiplication lambda x is a homeomorphism because the multiplication is continuous and inverse function is continuous. Now, since lambda x is a homeomorphism and if U is an open set, then clearly XU is also open, and again as X goes to X inverse is a homeomorphism, therefore if U is an open set, so U inverse is also open set. Similarly, we can show that right multiplication is also homeomorphism and therefore Ux is also open set when U is an open set. Now, to prove that AU is open for any subset A of G, it is sufficient to show that AU is equal to union of small a into U, where small a runs over capital A. Now, each small a into U is an open set and arbitrary union of open set is open. So, AU is open for any subset A of G. Similarly, we can say that U of A is also open set. Next, another important property of topological group is that every neighborhood U of identity contains a symmetric neighborhood V such that V product V is contained in U. To prove this, given a neighborhood U of 1, let V is equal to U intersection U inverse. Then it can be easily verified that V is a symmetric neighborhood. That means V is equal to V inverse and V product V is contained in U. This is also an important result about topological groups. If H is a subgroup of G, then so is closure of H. To prove this, one can use the convergency of net. That means one can take a net in capital H which is convergent, and then it is easy to prove that the point of convergency also is in H. Therefore, closure of any subgroup is also a subgroup. The following results are also of important in case of topological group. If capital H is a normal subgroup of G, then so is closure of H. Every open subgroup of G is closed, and if A and B are compact subsets of G, then so is A product B. In fact, C follows as product is continuous mapping in topological group. To prove A, let H be a normal subgroup of G. Then for any G in capital G, the set G closure of H, G inverse is closed and contains GH G inverse, which is equal to H as H is normal. Here G H bar G inverse is closed because both left and right multiplication are homeomorphisms. Therefore, we have that closure of H is contained in G closure of H G inverse. Conjugating by G, one also gets that G closure of H G inverse is contained in closure of H. As G varies all over the group G, the claim A follows. Now, to prove B, let H be open. So are all its cosets XH, since left multiplications are homeomorphisms. Therefore, its complement G minus H is the union of all these cosets except H itself. Hence, G minus H is open and therefore H is closed. This proves that every open subgroup of G is also closed. So far, we have discussed some properties of topological groups. All those properties we have discussed have been originated using left multiplication and right multiplication. In fact, using the homeomorphic property of left multiplication, right multiplication and inversion. Next, we shall continue with some more properties of topological groups which will be required in our study of quotient spaces. Next, we shall state another very important property of topological group. Let G be a topological group and let a subset of G be closed, and consider K subset of G be compact. Then AK is closed. To prove this, we use net. Let us consider a net in the product AK. So, the net can be expressed as AJ into KJ, where AJ belong to A and KJ's belong to K, and J runs over a directed set capital J. Now, let us consider that this net is convergent in G. We have to show that limit of this net also belongs to the product AK. As K is compact, one can replace this net with a subnet so that Kj converges in K, because we know in compact topological space every net has a convergent subnet. Now, since the composition in the topological group G is continuous and also inversion is continuous, the net Aj is equal to Xj into Kj inverse converges to, with the limit in A which is equal to closure of A as A is closed. Therefore, the limit of the net Xj is equal to Aj into Kj lies in the product Ak, which is therefore closed. So, this theorem says that if A is a subset which is closed and K is a compact subset of a topological group G, then their product is closed. So, the natural question, if we drop the compactness assumption in this theorem, whether this theorem remains true. The following example shows that we cannot drop the compactness assumption. For this, let us consider A is equal to set of natural number and capital B is equal to minus n plus 1 by n, such that n belongs to the set of natural number and n greater or equal to 2. Then both capital A and B are closed in R plus, but none of them is compact. Now, if we consider the set A plus B, then we get the product as 1 by n, such that n belongs to capital N and n greater or equal to 2. Clearly, this is not compact in R plus. So, in the above theorem, the condition that K is compact is necessary. Next, we go to prove some quotient space related property of topological groups. If H is a subgroup of a topological group G, then the set G by H of all left cosets of G acquires the quotient topology defined as the strongest topology such that the canonical projection map P from G to GH is continuous. In fact, I have already told about this. The set of all left cosets form a partition. So, the canonical mapping which carries G to its corresponding left coset gives a quotient topology on the collection of all left cosets. Thus, G by H has a quotient topology which is induced by the canonical mapping P and from the topology of G. So, we have the following properties corresponding to the quotient space G by H obtained from G by the canonical mapping P. Let capital G be a topological group and capital H be a subgroup of G. Then we have the following assertions. The quotient space G by H is homogeneous under G. The canonical mapping P from G to G by H is an open map. The important property is G by H is T1 if H is closed. Another important property is that the quotient space G by H is discrete if and only if H is open. Moreover, if G is compact, then H is open if and only if G by H is finite. Another important property is that if capital H is normal in G, then G by H is a topological group with respect to quotient operation and quotient topology. Here I like to note a point that if H is normal or not, then the quotient space G by H is defined. That means there G by H is a topological space. We do not know whether it is a topological group or not, but where H is normal, then the quotient group G by H is also defined and the quotient topology G by H also defined. Here, so G by H can be considered as topological group. Now let us come to the proof of these results. First, to prove that the quotient space G by H in respect to topology is homogeneous. Let us consider an element X in G acts on the quotient space G by H by left translation. GH goes to X GH. The inverse map takes the same form. So, to show that the left translation is homeomorphism of G by H, it suffices to show that left translation is an open map on the quotient space. Let U bar be an open subset of G by H. Here U bar represents a set of left cosets. Now, by definition of the quotient topology, the inverse of U bar under P is an open subset, say U of G, and it follows that the inverse image of G U bar under P is G U, also open subset of G. Therefore, G U bar is open and left translation is indeed an open map. So, this proves the first part of the proof. Next, to prove the second condition, let capital V be an open subset of G. We must show that P of V is open in the quotient topology on G by H. But P of V is open in G by H if and only if P inverse of P of V is open in G, as G by H has the quotient topology. By elementary group theory, we have P inverse of P of V is equal to V into H. Now, let X belongs to VH, then X is equal to V into H for some V in capital V and H belongs to capital H. Since V is open, given any element V in capital V, there exists an open neighborhood, say UV of V, such that V belongs to UV is contained in capital V. Thus, UV into H is an open neighborhood of X contained in VH, which is accordingly open. So, this proves that projection mapping here is an open mapping. Next, we shall prove that G by H is T1 if and only if H is closed in G. By general topology, G by H is T1 if and only if every single point set is closed. Now, if we can show that the single point set H in G by H is closed, then we will be done, because if we can prove that singleton set H in G by H is closed, then every left coset will be closed, as left multiplication is homeomorphism. So, to prove that G by H is T1, we have to show that H singleton set H is closed. Now, it is already given that H is a closed subspace of G. So, we have that singleton set H is closed, and therefore, every AH is closed. That means every singleton in G by H is closed. This proves that if H is closed, then G by H is T1, and conversely, if G by H is T1, then every singleton is closed, and therefore the singleton element H in G by H is closed. That means H is a closed subgroup. Finally, I shall prove that G by H has the discrete topology if and only if H is open in G by H. This proof also follows almost in the same way as the previous one. Now, if H is open in G by H, then every AH is open because of the left multiplication is homeomorphism. That means every singleton set is open in G by H, and therefore G by H has discrete topology. Now, to prove the converse, let G by H has discrete topology. We have to show that H is open. Since G by H has the discrete topology, therefore singleton H is open. So, this proves the converse. Now, if H is a normal subgroup of G, then G by H is in fact a group, and we have already got the quotient topology on the quotient space G by H. Now, it can be easily verified that the operation, that means group operation on the quotient space G by H are continuous, and also the inverse operation on the quotient space G by H also continuous. So, G by H form a topological group. Next, we prove that for any open symmetric neighborhood V, the set H is equal to V to the power n, where n is equal to 1 to infinity is open subgroup. To prove this, let V be a symmetric unit neighborhood That means a symmetric neighborhood which contains identity element. Now for any x belongs to v to the power n and y belongs to v to the power m, one has x y belongs to v to the power n plus m, and as v is symmetric, one also has x inverse belongs to v to the power n. So v is an open subgroup. Finally, we shall prove that if G is a topological group and H be the closure of singleton set 1, then the following hold. The set H is the smallest closed subgroup of G. The group H is a normal subgroup and the quotient G by H with the quotient topology is a T1 space. All of these results follows from the previous theorem. Secondly, every continuous map of G to a T1 space factors over the quotient space G by H. This also follows from the previous theorem. Finally, every topological group which is T1 is already T2, that is Hausdorff. I am leaving this proof of this part as an exercise. So far we have discussed various kinds of properties of topological groups. In fact, most of the properties are due to the fact that left multiplication, right multiplication and inversion are homeomorphisms. We can formalize some properties. One of them is that a G by H is T1 if and only if H is closed, and G by H is discrete if and only if H is open. The topological group will be useful in constructing new types of quotient space, which will be discussed in our next module. With this, we end this module. Let's pass to next module.